From last time we had these properties about determinants, and I think it might be good to see how useful they are if we're actually looking for determinants. So what I wanted to do is just to recap some of these properties and see how useful they might be when we actually try to look for determinants. So I'm going to take a quick shot of some of these properties. We have a couple of lemmas. And some theorems. And then a bunch of other properties. Is there another one? There's one more. See if I can get this to fit in one page. Kind of small font. So here are a handful of properties, so it might be good if we can just browse through them and then look through some problems where we have to find some determinants of things. So let's start off with properties or determinants of elementary matrices. Some determinants of elementary matrices involve an elementary row operation would be switching a row. And whenever we switch rows, we have an elementary matrix of a row switch, and the determinant of that is -1. So based on this theorem 4.4 and this lemma 4.5, if we have a matrix, we're trying to find the determinant of that matrix, we do a row switch, we're going to incorporate a negative sign. If we multiply one row by a constant, a scalar, then the determinant of that will be multiplied by k. And then if we multiply one row and then add it to another row, then the determinant of that elementary matrix is 1, which means if I do something like that, a row operation like that in my original matrix A, then I'm just going to multiply the determinant by 1. And I'm saying that multiplying by a determinant of 1 because of this lemma here. And so a few other pieces of information. If you have a matrix that's invertible, then the determinant is equal to 0, which means if the matrix is not invertible, then the determinant has to equal 0. If it is invertible, then it's not equal to 0, the determinant. Multiplying a whole matrix by k is multiplying n rows by k. And so there's n of those k's that we're multiplying. And the more general is that the determinant of product is equal to product of the determinants. And then you have this other invertible matrix. And then the transpose of a matrix will give you the same determinant. All right. Let's see if we can do some simple problems. Oops. Let's pick I don't know, one of these. Let's do number 2. And there's several ways to do this. One way is to just expand on a particular row or column, but I want to try to take advantage of some row operations and things like that, and show you how that might work for finding determinants of a matrix. So let's find a determinant of this matrix by doing some row operations. By the way, we also have this other, I don't know if it was a theorem or what, but if we had an upper triangular or lower triangular matrix, then the determinant is just a product of the diagonals, right? That was a what?
That was a good one.
That was a good one. So let's see. Let's do some elementary row operations. I'm going to. We don't have to do this, but let's switch the second and third rows. So R1 switch with R2, and technically this is a matrix row operation. So let's do the determinant later. So row operation that switches rows: 1, 0, negative 2. 0, minus 1, 1, and 3, 3, 2. Okay. I switched 2 and 3. 2 and 3. Yeah, thanks. Next, I want to, we can do a couple of row operations at this step. I'm going to multiply the first row. I think we need to do this in two different steps. Multiply the first row by negative 3, and then add it to the third row. So if I do that, I'm going to get 0 for this, and then 3. I guess I could have done it here. And then by negative 3, that's positive 6. Added to 2 is 8. Is that correct? And then one more to get rid of this. Let's multiply the second row by positive 3 and then add it to the third row. So 1, 0, minus 2, 0, minus 1, 1. And this becomes a 0, 0. And then 3 plus 8 is 11. Okay. So with 3 elementary matrices, we went from this matrix A, let's call this A. So matrix A is actually, well, this new matrix, let's call this U because it's upper triangular. U is actually equal to matrix A and a couple of elementary row operations. So an elementary row operation that switches rows, let's call that E1. The elementary row operation that takes the first row, multiplies it by negative 3, and then adds it to the third row. Let's call that elementary row operation 2, E2. And then elementary row operation 3 is this one where we take the second row, multiply it by 3, and add it to row 3. So it turns out that our U is equal to this. Which means if we solve for A, these are all invertible, right? So do you remember the order that this is supposed to go? Inverse? If I want to take the inverse of this thing and so I can have it on the other side, you remember how that goes? So U so I have the E's on the right side or on the left side? So if I want to peel out if I want to do it one at a time, I would multiply it by the inverse of E3 on the right first. And then that would give me U times E3 to the negative first power to inverse of E3. And then, so E3 would cancel, and then I would do E2, and I would do E1. So the inverse of a product of matrices is the product of the inverses in reverse order. And if it's done on the left side, then it has to be done on the left side on the other side. So the determinant of A is equal to the determinant of this big mess over here. I guess I shouldn't use. And the determinant of a product of matrices is equal to the determinant of each of these things individually. And then the determinant of inverses, if you have an invertible matrix, is the reciprocal So I probably didn't need to do all this work, but I think I'm just trying to illustrate, trying to use as many of those theorems and lemmas and properties that we saw as much as possible. Elementary row operation E1 is what? E's. These are all E's. So the elementary row operation E1 is a switch of rows. Do you remember what the determinant of a row switch is? -1. The second row operation is multiplying a row by something and adding it to another row. What's the determinant of that? Do you remember? 1. And then the same thing for the last row operation. And the determinant of an upper triangular matrix is what? The product of the diagonals, which is 1 times -1 times 11. So if we do this multiplication, we really just have -11 times -1, so it's +11 is your determinant. Okay? So in this example, we took advantage of being able to row reduce and then looking at those elementary matrices that was needed for the row reduction. And I don't think we ever really need to multiply a matrix by, unless you really want to multiply a matrix by, to have the diagonals to be equal to 1. You don't need to do that row operation where you multiply the whole row by -1 or by 1/11 or something like that. But once you get it to a diagonal and you know that the determinant of an upper triangular, and you know the determinant of an upper triangular matrix is just the product of its diagonals. What? The determinant of U is 1 times -1 times 11, right? Determinant of the third elementary row operation that we did is 1. Determinant of the second one that we did is 1. Determinant of the first elementary row operation that we did is -1. So I have this -1 and then this -1 that made it a positive. No, because determinants can be positive or negative depending on what your thing is. This is the determinant of A, which is what we're looking for. We don't care about all this other stuff. This other stuff is really to help us find the determinant a little bit easier. Now we could have taken A and expanded on a row or a column or something like that, and we should still get the same result. What? Sometimes it's faster if you're quicker at doing elementary row operations, as long as you keep track of the row operations that you did. And whenever you do this, row operation where you multiply by something added to another row, it has no contribution to your determinant. It's just one. So as long as you can do that and find the product of the diagonals of your results, then seems like that would be an easy route. All right, I'm tempted to do this determinant by expanding over a row or column, but I don't. It's more time than what we need to spend on. So you guys can do that if you want, and you'll see that you get positive 11. All right, a few more things from this section before we move on. The submatrix, or the cofactor they call it, is the submatrix after you cross out a row and a column of a particular element in the matrix. And they also include whether it's positive or negative. So that helps in the expanding over a row or column business. And somebody asked about Cramer's rule the other day. Cramer's rule so let me put this definition of the cofactor. But Cramer's rule is a way to solve for systems of linear equations, or you can look at it as, if you want to look at it in the language of matrices, it's a way to solve for a matrix times some unknown vector is equal to another vector. And we solve for this by replacing, and this looks a little confusing the way it's done, so I think it might be better to look at the algorithm of solving for Cramer's rule, or solving for a system. Let's see if I can get an example here. No, there's no example. Let's just make one up. Homework? Which section? 4.2. Oh, this is going to have the answers. Let's view it so we don't see the answers. No, they're just 2x2s. I was going to do 3x3. Oh, let's do this one. Why not? So if we have a system of linear equations that look like this, we're asked to use Cramer's rule to find the solution. Actually, I'll put it in the previous page where we have Cramer's rule. So this looks a little confusing, but what this is saying is that to apply Cramer's rule, we're going to take a look at the A matrix as a matrix of coefficients, and then the x vector is equal to the B vector, which is in this case the right-hand side, 5 and negative 14. So the matrix of coefficients is 2, minus 1, 1, and 5. And what they're saying here is to find the first element here, x. So x the vector x is really x comma y or xy or however you want to look at it as a point or a vector or column vector or row vector or whatever. But to find the first component of your solution, what we want to do is we want to take the determinant of the 2 by 2 matrix here, where the first column is substituted with your B vector. So 5, negative 14. And then your second column, and if you had more columns, then your other columns will be just whatever they are originally. So that is the first column over here was replaced by the B vector. That's what this numerator is saying. And then your denominator is going to be the determinant of just whatever the original matrix is. Okay? So this is going to give us 10 minus 1, so that's 11. And then this is going to give us 25 minus 14, which is 11. So the first component should be 1, or 11 over 11. And then, yeah, to get the y, you're going to, I guess I don't need the DET here, huh, since I'm going to use the vertical bars. So to get the y component, that's y or x2 according to the formula. You're going to take the determinant of your matrix where you're going to replace the second row by your vector b, your vector b. So that's 5, negative 14 for that column. And then the denominator stays the same. So what's this going to turn out to be? This is negative 28 minus 5, negative 32, 33. And this is the same one, 11. So that looks like it's going to be negative 3 for your y value. What? I hope so. I think my answer should be 1 comma negative 3. And we'll check that right now. And with something like this, you can also, you can use the coefficient with the, what do you call it when you add on? Augmented, the augmented matrix. Starting to confuse all these terms. You can use the coefficient of matrices and then the augmented B matrix or B vector, and then you can row reduce, and we're going to get the same results.
So,
yeah.
Who cares about Kramer's rule? Why is it interesting? It seems like it's just weird.
It's
sit around figuring out a bunch of determinants and you can do elimination.
Well, that's what they say in the book. Kramer's rule is not really. It's just for kids.
Some of this stuff was more interesting when computers were around because everyone only did like really small sample problems.
Right. Well, we could take a look at a quick application of Cramer's rule where Cramer's rule might be interesting of some use. But I don't want to do that. Okay, well, a quick diversion of Cramer's rule, and some of you might find this familiar. Define the Wronskian of F1 and F2 to be W F1, F2, this is 1, F2 equals the matrix F1, F2, F1 prime, F2 prime. Does it look familiar? Okay. No. Yeah, derivative, the prime is derivative. I say this is familiar because this is something that we did in our differential equations class. So for those people who are in my differential equations class, this is what we have. So what we're essentially doing is we're finding out whether this is whether F1 and F2 are linearly independent, and we're going to say that F1 and F2 are linearly independent if this thing doesn't have a solution. So if how's it going to go? Alpha F1 plus, wait, I think I lost it. I think what we want to do here is we want to, I forgot. Yeah, we want to show, oh, they're linearly independent if this is equal to 0, but we're going beyond that. We're trying to solve for a linear combination of F1 and F2. Why don't we skip over this for now? I failed at my example. Oh, no, because your system is going to look like this. So F1, F2, F1 prime, F2 prime. I think we use U and V, or U1 and U2. And this is equal to, no, sorry. This is Y1 and Y2, and this is equal to U1 and U2. So we're trying to solve for solutions for our differential equation of the form y1 plus something with y2, and they involve derivatives. But to find the solutions for this, y1 is going to have to equal to, according to Cramer's rule, y1 is going to be equal to the determinant of u1, u2, and f2 prime divided by the determinant of the original Wronskian. And this is equal to U1 F2 prime minus U2 F2 divided by, let's just call this W for Wronskian. And then Y2 is going to be similarly defined as F1 F1 prime U1 U2 divided by the determinant of the Wronskian. So this numerator is going to be F1 U2 minus F1 prime U1 divided by the Wronskian down there. So this U1 and U2, or Y1 and Y2, are supposed to be the solutions that we're looking for. And what we did here is we essentially used Cramer's rule to solve for this. Okay? So if we're dealing with matrices with just scalars, whether they be real or complex, or even if we're in Z, whatever, then Cramer's rule doesn't seem like it's of any use, because we have, all kinds of other tools to find solutions for these things. But if you have a stranger problem that looks like this, and this is just for a 2x2 matrix, technically we can have a 3x3 matrix of functions like this as well, and so that is where Cramer's rule might be a little bit more important. I don't know how much of this we're going to get into in our class, but it would be useful if you're going to go into engineering and where you have to take differential equations. And so these ideas of matrices and solving for matrices this way would be important. Actually, you might have easier ways to solve for this instead of Cramer's rule, which begs the question, what use is this? Anyways, let's go past that now. And move on to there's a problem, or a couple of problems that I thought was kind of interesting that might be good quiz or exam questions. Remember those K's in the first test?
Oh, that's nice.
Okay. Let's do one of these problems where we have to solve for K to see if it's invertible. And remember, with determinants, it's invertible if and only if the determinant's equal to 0. So it's just a matter of probably finding some polynomials and setting them equal to 0, or finding out when they're not equal to 0. So let's do one of these problems just for fun. I don't know, pick one. 45, 46. 45. All right. So we can do this using some of the determinant formulas that we were looking at, or we can just go through it and expand on a row or a column. And then, because essentially we want to find the determinant of this, right? So we want to find the determinant of A. And we could do that by row reducing and things like that. But let's just expand over a row or a column. And there's a 0 here, so I think I might be interested in expanding over the first row to get our determinant. So the determinant of A in this case is going to be, let's see, we start off with the K, and then we take its submatrix. So let me write it out first instead of trying to find the determinant right there and then. And then we have a second term at 0, but since it's 0, then we don't have to worry about the other matrix here. This is a minus sign, not an equal sign. And then plus, and then we have a K for this one, and then we expand over and get the submatrix minus k 3 and k plus 1 1. All right. So let's see what this polynomial is going to look like. We have k plus 1, k minus 1. I think that's k squared minus 1. And then minus negative 8. 0, and then we have a k. And then this is going to be minus k minus 3k plus 3. Or let's just say plus 1 and then distribute the negative 3 in a minute. So if we work out this first one, this would be k cubed plus 7k. Is that right? And then this next one, let's leave the k out here. Let's do this in a couple more steps so I don't mess up. We have a minus k minus 3k. I think that's negative 4k. And then minus 3. So k cubed minus 4k squared plus 7k minus 3. Oh, that doesn't look like it's going to... I was hoping it'll... Oh, minus 3. Oh, 3k. So that... It'll be what? 4? 4k? Okay. All right, so that's nice because now we can factor out a k. We got k squared minus 4k plus 4, and I think that factors to k minus 2. So this is equal to 0 when k is equal to 0 or k is equal to 2. So it looks like if as long as k doesn't equal to 0 or as long as k doesn't equal to 2, then we have an invertible matrix. So A, we can conclude A is invertible if k does not equal to 0 or 2. Okay? If it was equal to 0, your determinant's equal to 0, which means it's not invertible, and then that's it. When k equals 0 or k equals 2. Yeah. Yeah, that also would have worked if we did row operations and then... I think so, because we have k's and stuff that look like it might be... I mean, having this 1 0 here makes it easy enough to expand on a row. If I didn't see any zeros, then I might want to do some row reducing. Okay, good? Good. All right, so this determinant business is really just a little sidetrack on what we're really wanting to do, which is finding eigenvalues and eigenvectors. So we're going to go back to finding eigenvalues and eigenvectors. And we talked about this already at some point before we started this, while we were still in the first section in chapter 4. We talked about this idea that if we take a matrix and subtract lambda I from it, then we're looking for the null space of that particular set of vectors to find, or that the null space of this this new matrix to get us our eigenvalues. So to find eigenvalues and eigenvectors, here's a step-by-step process. We want to compute the characteristic polynomial, which is a polynomial in lambda. Lambda is going to represent your eigenvalues. So the polynomial is found by finding the determinant of this matrix, A minus lambda I. And then once you solve for that characteristic equation, you're going to have your eigenvalues. I think we've gotten that far. And I think we also went and found eigenvectors by putting this eigenvalue. So you're going to have eigenvalues. Now you might have 0, 1, 2, or 3, depending on what your n is, or more, up to n. But you need to take each of those eigenvalues that you found and you put it back into this matrix and then find the null space of that to find your eigenvectors. And if you just have one eigenvector, then that's enough to span the eigenspace. If you have two, then make sure they're linearly independent and then find out the span of that. So really, this is the recipe for finding eigenvalues and eigenvectors. Okay. Let's see if there was a theorem here that's worth looking at before an example. Let's jump to doing an example. Well, I don't have any examples here. Do I have a book? So let's take one of these examples. Let's see. Let's do a 3 by 3 matrix. Let's find the eigenvalues and eigenvectors for this matrix. Okay, so the process is to come up with this polynomial, A minus lambda I. And then we want to find the determinant of this and then solve for this when it's equal to 0, solve for lambda. So let's do a lambda I. It's just going to be lambdas in a diagonal. So when you subtract this, and you'll do this enough times, when you subtract this, you'll see that you'll just look at the original matrix, and then just along the diagonals, you'll have a minus lambda associated with these things. So we have a 1 minus lambda, 2, and 0, -1, -1 minus lambda, 1, and 0, 1, 1 minus lambda. Okay? Now you want to find the determinant of this. And you can do this in a lot of different ways. We can expand on a row or a column. I think anything with a 0 would probably be good to expand on, so I'll just take the first row. We've got 1 minus lambda times the submatrix determinant minus 1 minus lambda, 1, 1, and then 1 minus lambda. The next one in our expansion along the rows is a 2, but then you have to, since it's a second element in the row, we're going to take the negative of that. And then if you cross out the first row, second column, your determinant, your submatrix is going to be minus 1, 1, 0, 1 minus lambda. And then the last element in that row is 0, so we don't even need to worry about what happens after that. So the determinant of the first submatrix is going to be minus 1 minus lambda times 1 minus lambda minus 1. And then the determinant of this next one is going to be negative 1 times 1 minus lambda minus 0. So that disappears. So let's expand this first one. This is really 1 plus lambda with a negative in front, and then 1 minus lambda. So that's 1 squared minus lambda squared with a negative in front, minus 1. We'll see how that works out in a minute. Negative 2, and then we have minus 1 plus lambda. Probably taking too long to do this, huh? Just punch it in my Mathematica and get the answer. I have lambda squared positive now. Minus 1 is minus 2 being added. And then here we have a positive 2 minus 2 lambda. Foil this out. I'm going to get a lambda squared minus 2 minus lambda cubed plus 2 lambda. So looks like things are going to go away. And then all we have left is lambda squared minus lambda cubed, which is going to give us eigenvalues of 0 and 1. And it looks like 0 is multiplicity 2. Okay. So those are the 2 eigenvalues. Now this is a 3 by 3 matrix, and we have 2 eigenvalues. And so one would expect that one of the eigenvalues would have a 2-dimensional eigenspace. So we'll see that happen, hopefully. Okay, we good so far? So let's continue on with this. On to the next page. We'll have this information next to us so that we can use it, make use of it. And we have to treat each eigenvalue separately. So let's take our eigenvalue of 1 first. And let's see if we can find the eigenspace for that, a corresponding eigenvector. So when lambda is equal to 1, we're essentially going to be looking at this matrix over here and put lambda is equal to 1. And so we get A minus lambda I is equal to 0 to 0, negative 1. Is this 0 again? No. Negative 2? 1, 0, 1, 0. So what we want to do is that we want to, let's do this on the side, what we want is a minus lambda I times x is equal to 0, and we want to find out x, which is the same thing as finding the null space of this matrix. And so if we want to find the null space of this matrix, we can do the augmented. And then just solve for this. Oh, thank you. Probably want to shuffle things around, and I think we solve for this by making it what do you call it? Row reduce thing. -1, -2, 1, 0. So I'm going to move the first row up. And there are no consequences for switching rows here. It's not like we're doing some LU decomposition or finding determinants. We're just solving for the system. So I'm going to switch the second and third row also. And then I'm just going to wipe out the third row by just doing another elementary row operation. These shouldn't be equal signs. These should be arrows. And -1, -2, 1, 0, 0, 1, 0, 0, and this one will just disappear. So if we solve for this, we can do x1, x2, x3, or x, y, z. What? x1, x2, x3. So we're going to have a free variable in x3 if we get this set up. So let's continue to solve for this. In this little space over here, we got -x1 minus 2x2 plus x3 equals 0. We're going to have x2 equal to 0. So I'll box that up, and I know that x3 again is a free variable. So that would make x1 minus x1 minus 2 times 0 plus t equal to 0. So x1 is equal to t or negative t? Positive t, yeah? So if you just let t equal to 1, then you have 1, 0, 1 is your vector. So x1, x2, x3 is going to be t times 1, 0, 1. So you can take a look at this expression as a span of 1, 0, 1, or 1, 0, 1 is a basis for this eigenspace. Yeah?
What's the point of having the zero augmented matrix if we never manipulate the zeros?
Oh, nothing. It's just that this is how we're computing it. Yeah. I mean, you can just ignore the zeros, and at the end, remember that there are zeros there. So, eigenvector 1, 0, 1. Eigenspace. There's a notation for that. They say E for eigen space, and then the sub 1, the 1 refers to the eigenvalue, and this is going to be the span. Yeah, sorry. So the eigen space for this particular eigenvalue is a one-dimensional space, so it spans a line, and then these are your other pieces of information. Questions? Okay, now we need to do the same thing. We need to do the same thing for our second eigenvalue, 0. So let's do that. Where's my...
What if you have two free variables?
Then your eigenspace will be two-dimensional.
For one,
For one eigenvalue. So let's explore this eigenvalue, eigenspace, and eigenvector for this. Let's see. A minus lambda I. Lambda is equal to 0, so we got a 1, 2, 0, negative 1, negative 1, 1, 0, 1, 1. And then we want to row reduce this and find the space. So 1, 2, 0, minus 1, minus 1, 1, 0, 1, 1. Let's find the null space of this. Let's see. I want to add the first row and the second row. So this is a 0. This is a 1. This is a 1. And then 0. And then we see from this step that the second and third rows are exactly the same. So we have x1 plus 2x2 plus 0 is equal to 0. We got x2 plus x3 is equal to 0. Free variable at x3. x2 is going to be equal to negative x3. And then x1 is going to be equal to negative, positive 2t, right? So it goes in, it becomes a negative 2x, but negative 2x2, but x2 is equal to negative t, so it becomes a positive 2t, right? Okay. So then your x1, x2, x3 vector is going to be 2 minus 1, 1. So it's again one-dimensional. I thought this was going to be a 2D. Well, I thought there was going to be two independent parameters. I thought I was only going to have one row and everything else would be 0, but it didn't all disappear. Unless I did something wrong here. Did I do something wrong? Usually it's the copying business that it's those zeros. So I think this is right. So the E vector 2 minus 1, 1, and then so the space is going to be the span of 2 minus 1, 1. solve for these things. They have their uses. We're going to, well, again, going back to differential equations, we're going to get to a system of linear differential equations where we're going to need to use eigenvalues and eigenvectors to find their solutions. Okay. So that was that. I noticed when I was reading this problem, they were looking for an algebraic and geometric multiplicity of each eigenvalue. So we didn't really define that, and I was looking for that in my notes, and I don't think I have that definition in my notes. So it turns out that when you first solve for the when you first solve for this, the determinant of this matrix over here, it's called a characteristic polynomial. When you solve for that characteristic polynomial, its multiplicity is going to be your algebraic multiplicity. So for each of these eigenvalues, you're going to get your eigenvalue, lambda is equal to 0, that has algebraic multiplicity of 2 because it's a repeated root, and eigenvalue 1 has algebraic multiplicity of 1. Now, to get the geometric multiplicity, what you need to do is you need to essentially find the dimension of the eigenspace, or figure out how many eigenvalues are associated with it. So in this case, when lambda is equal to 1, this has geometric multiplicity of 1 because its eigenspace is one-dimensional. And this eigenvalue of 0 has geometric multiplicity of 1 also. It's more likely to happen that the geometric multiplicity and the algebraic multiplicity are the same, but in this case they're different. So it does happen when they're different. Roman?
What's the geometric multiplicity of the other eigenspace that we have?
It's 1 also because it's one-dimensional. So for lambda is equal to 1, we went through the work and we found one eigenvalue associated with it. For this, I was expecting to have 2 eigenvalues, but we ended up with just 1, so this has a geometric multiplicity of 1 also. Because you only have one eigenvector. Okay. All right. So let me just put up a handful of theorems from this section. The eigenvalue of a triangular matrix, eigenvalues of a triangular matrix are the entries on its main diagonal. That's because if we find the determinants of this, well, you can kind of see, you can work it out. A square matrix is invertible if and only if 0 is not an eigenvalue. Oh, that must mean the matrix we worked with was not invertible. That's why those weird things happen. Wait.
Isn't like 0 always the solution?
Hmm?
Isn't the 0 vector always the solution? Or no, that's an
The 0 vector, yeah, the eigenvalue. So I think last time when we were talking about determinants, we said that we were going to add a couple of things to our list of the fundamental theorem of invertible matrices. And I think last we stopped off here. And so the two other things to add on as we're talking about determinants and eigenvalues is that if your matrix is invertible, then determinant of A is not equal to 0. And if your matrix is invertible, then 0 is not an eigenvalue of A. So in our case, we got 0 as one of the eigenvalues. And so if we were to check to find the inverse of that matrix, we wouldn't be able to because it's not invertible. Okay. All right. There are a couple more things to add on, but I think we'll add this on next time. So I have a couple of announcements for the class. Is a class in general. In web access, I have a place for you to make up exam 2. And people were asking about that. If you're interested in making up the second exam, you can download the test from here, do it. And I'll collect it on Monday when we get back. And then I'll grade it, and I'll take the average between this and your other exam. The other thing that is due on Monday is that we haven't had a quiz here in a while, so I have 2 quizzes for you to do, but it's a take-home quiz, so it's something that you need to print out and then do by hand. So quiz number 6 and quiz number 7 are related to pretty much the things that we were working on today. Finding determinants, and quiz 6 is about finding determinants, and quiz 7 is about finding eigenvalues and eigenvectors. This is for Monday as well. So you guys got a lot to do between now and Monday. Good thing you have the whole week to do it. And we don't have class on Wednesday, so I'll see you guys after Thanksgiving.